Hey everyone, how are you guys doing? Yeah, so you have heard a lot of very exciting new stuff from the previous amazing speakers, and I'm going to talk about something that's already existent, but hopefully equally exciting. This is how we build the most scalable blockchain. So from the very beginning, Near started with this vision of building fast, cheap protocol that can scale to meet the needs of billions of users, and now also AI agents. And the primary way we achieve this is through blockchain sharding. So blockchain sharding is basically this scaling approach that divides the global state of blockchain into shard states so that no validators in the network need to track the state of all the shards. And as a result, the network can scale with the number of shards it has. Oh, sorry. So back in 2019, we came up with this Nightshade design for a completely sharded blockchain. And before that, all the prior art on blockchain sharding pretty much is what we show on the left-hand side, which is that you have one beacon chain, and for each shard, you have a shard chain. And there is some complex orchestration mechanism so that allows you to communicate between different shards. But it's actually very difficult to implement because when you have one blockchain per shard, then it can have its own forks. When you want to communicate between two shards, you need to think about which fork it's coming from and which fork it lands on and what happens if it gets reworked. All of those problems do have some solutions, but it requires very complex machinery to make it work. And one of the key innovations we did with Nightshade is that we say, well, instead of having that complexity, how about we just have one chain that rules them all? So this one chain that has blocks that contains chunks, which are shard blocks from each shard, and this greatly simplifies the design. And this is what we did back in 2019, the first version of Near white paper. It's designed for complete sharded blockchain and has this asynchronous execution environment. If you want to communicate between two different shards or doing cross-contract call, what happens is that it first gets executed on the source shard, and a receipt would be generated and sent to the destination shard. And the security relies on fraud proofs, and this is how you guarantee that no nodes need to track all the shards while still maintaining the security of the network. Now, 5 years later, we made a lot of progress on implementing the original Nightshade vision, but over the past year or so, we did a major overhaul to the Nightshade design by introducing stateless validation. And this is basically the foundation for the Nightshade 2.0 that we introduced this year. The reason for introducing stateless validation is threefold. So one is because in practice, it's actually very difficult to implement fraud proofs and to test them, make sure that they're bug-free. And there is a very good reason why in the optimistic rollout world, people are still struggling with deploying them into production. And two is that it actually significantly improved the single shard performance. This is because before, the biggest bottleneck we have on single shard performance was state access. And the reason why there was a problem was mostly because you have to do a lot of disk reads, and that really slows things down. So with this design, we actually make sure that the state is entirely held in memory. We achieve this by having this twofold approach where on the chunk producer side, because we only need a few of them, they can run more expensive hardware, and as a result, they can hold the state of an entire shard in memory and produce chunks, execute chunks by having the state in memory. And then on the validator side, because they receive state witness, they don't actually keep any state locally, it's naturally the case that the state is held in memory when they execute the chunks. And as a result, because the validators don't need to hold any state locally, they don't need to run as expensive hardware. In fact, they can run pretty cheap hardware. And this gives rise to better decentralization, meaning that we can have a lot more validators on the network. And this is not just something that we designed and put into some kind of white paper. Actually, over the past year or so, the team worked very hard on implementing this, and we launched in August 2024. This is the biggest upgrade we did to mainnet since the original launch in October 2020. In terms of lines of code, probably like over 100,000 lines of code changed. This huge upgrade was done completely live and with 0 downtime. So as a user, as a user, you probably didn't even know that this upgrade happened, and has to rely on us like telling the story that this thing actually happened to know that, well, the mainnet has been successfully upgraded to this whole new version. And now mainnet is fully sharded. Both state and transaction processing are sharded, meaning that no validators need to track the state of more than one shard. And today we have 6 shards on mainnet. So that's a pretty good state to be in. But in my opinion, that's just the beginning of a whole new era where we want to explore the limit of scalability. We truly don't know today where the limit lies, because in theory, the mainnet can scale with the number of shards. And not only that, we actually also want to build this interesting feature called dynamic resharding, where the number of shards on the network would dynamically adjust based on transaction load. What that means more concretely is that if you have one shard that becomes congested, let's say there's like a popular app launching there, then the system would detect that and knows that it should split that shard into 2 shards. And conversely, if you have 2 shards that are both idle or low usage, then it would merge them back into one. So let's imagine in this bright future where we have 100 shards, and each shard can do 10,000 transactions per second, and that would result in 1 million transactions per second, which is 86 billion transactions per day. It's a huge number, and we do need that if you think about the bright future that Ilya, Alex, and other speakers have talked about, where we have billions of users and agents, or maybe even trillions, transacting, settling intents, and payment channels. This requires unparalleled scalability that only Near can offer through this sharded approach. And it's not enough to just have that 1 million transactions per second or 86 billion transactions per day. You cannot settle all the billions of intents per day inside one single smart contract. That just would be too much for one single smart contract, which lives in one shard, to handle. So what we need is actually sharded smart contract, which allows us to fully leverage the power of Near's sharding, so that instead of it existing on one shard, it simultaneously exists on all shards of Near, so that basically, no matter how many shards Near has, the smart contract would be living on that many shards. This is possible by making the smart contract code global, meaning that every single shard has access to the smart contract code, and the state is actually stored under user account rather than today stored under the contract account, which then have to live in one shard. And this means that it can fully leverage Near's sharding approach and be much faster and also much more scalable, and allow for this non-blocking peer-to-peer or multi-party settlement, which is key to this future. We'll have like tons of agents transacting with each other. So that's great. I talked a lot about how Near is scalable, how we can make it more scalable, but we also wanted to make it even faster than today. So today, it's pretty decent. The block time is about 1 second, and time to finality is about 2 to 3 seconds. But to make a truly seamless experience for the users, we want to do better. And one of the primary ways we want to do this is through the separation of consensus and execution. That may sound very abstract. So what that means is that today, one of the problems we have is that when you need to execute something, you first need to wait for the consensus to create a block, and then you know what to execute. That's a problem because it means that the nodes are not constantly executing transactions or receipts. It has to wait. Rather, what we want to do is that we want to have consensus run as fast as possible, just all those transactions, and then separately, the executions try to catch up. This means that a node would be constantly executing transactions because you know what to execute. It's already there, waiting for it to execute. This would allow for much better throughput, but also would support long-running transactions because now you don't need to have a state root update every single block. And because blocks are produced much more frequently, if you have those RPC nodes, just eagerly execute them as they get produced, you also get optimistic confirmation that's much faster than what we have today. And that is enough for most people. And then separately, we still have the finality guarantees that we have today. So that's also not the end of it. So if you actually think about it in a more concrete way, like what this kind of thing actually enables, so on the bottom, you can see what we have today. So let's say you have some transaction that missed the block production, let's say got in like 1 millisecond after the block's produced. Then it's kind of suboptimal because you have to wait for 1 full second until the next block gets produced. Rather, if we have this separation of consensus and execution, the consensus just constantly runs, you can produce blocks much faster, and let's say blocks are produced every 200 milliseconds, then even if you miss the block production, you know that it will get in 200 milliseconds later, which is 5x better than what we have today. And what's more interesting is that it allows for this long-running transactions that doesn't fit in the limit of 1 block. So that is not possible today because we need to make sure that consensus can continue producing blocks and not get interrupted. So that there is a gas limit that essentially limits how much time each block can spend on execution. And in this new world, because you don't actually need to have the state root update going into the consensus for the next block, you can actually wait longer than 1 block or even 2 blocks to wait for some transaction to finish. And this is very interesting because it enables use cases that are not possible today. For example, we have Aurora running EVM interpreter as a smart contract, and Alex has come to me at least 100 times saying that, hey, like how can we make sure that 1 transaction can fit more gas into it so that we can be fully compatible with Ethereum executing 30 million EVM gas in 1-year transactions. So this is basically the solution to that. And on top of that, still the use cases we support today, let's say ref swaps that takes 5 milliseconds, that's also readily available and also much faster. So this, combined with what we already have with Nightshade 2.0, this leads to a very bright future where not only Near is hyper-scalable, but also extremely fast and very versatile. You can build all kinds of different applications, whether it's decentralized exchange that does some swaps, it's very fast to execute, or some long-running computation that takes seconds to execute.